Okay, the topic is electric potential and potential difference. So, first, in order to actually understand the meaning of potential and potential difference, we need to first start systematically, right? We need to understand first the line integral of electric field and its physical significance. We are already aware of electric field. So, line integral of electric field, what's the significance of this? So, let's deal with this particular topic first. So, what we do is, we assume a source charge to be located at the origin, say. This is the x-axis, suppose this is y-axis. Now, this source charge is considered to be positive. So, electric field would be in the outward direction, and for a point charge, the electric field is spherically symmetrical. So, its field lines would be somewhat like this. I am plotting the field lines only in the first quadrant. So, these are the field lines. It will be in the radially outward direction. It emanates from the positive charge and make an angle of 90 degrees with the surface of the charged body, right? Suppose we consider any 2 points A and B which are lying under the influence of the electric field due to this source charge. Let AB be any arbitrary path, and also assume the position vector of point A be RA vector and the position vector of point B be RB vector. This is any arbitrary point B. Now, in case I place a point charge over here, then definitely this point test charge will experience an electric force of repulsion due to this source charge. So, it will experience a force along this direction. This would be Q naught E. This is the force experienced by this test charge under the influence of electric field due to this source charge, right? This is the direction of the electric field, and this is the direction where it will experience the electric force, right? So, electric force experienced by this test charge Q naught at point P under the influence of the electric field due to this source charge located at the origin would be given by Q naught E vector. Now, in case we consider the test charge to be unit positive test charge, then E vector would be equal to F vector. So, theoretically, we can say that electric field is numerically equal to the electric force experienced by a unit positive test charge placed at point P. Fine. Now, suppose this test charge is to be moved from P to Q through a very small distance, suppose dl. So, small amount of work has to be done, and that small amount of work done is given by the scalar product of force and displacement. So, over here we will write F vector dot dl vector. In case the unit positive test charge will consider Q naught to be 1, so F would be equal to E. So, in that case, it will be E vector dot dl vector. So, what I mean to say is that E vector represents the electric force experienced by unit positive test charge placed at point P. E vector dot dl vector represents the small amount of work done in moving unit positive test charge from point P to point Q through small distance dl. Now, what about the total amount of work done in making this charge Q naught in moving from point A to point B? That will be given by integration of this. So, total work done would be given by integration of dw. So, it will be E vector dot dl vector. A to B. A is the initial point, B is the final point, whose position vectors are respectively RA and RB. So, write the limits as well, RA to RB. This term represents the line integral of electric field. So, regarding its physical significance, let's repeat it. E vector, that is electric field, represents the electric force experienced per unit positive test charge placed at point P. This is the first step. E vector dot dl vector represents small amount of work done in moving this unit positive test charge from point P to Q through elementary distance dl. This is the second. Third, integration of E dot dl. This term is known as the line integral of electric field, and it represents the total amount of work done per unit positive test charge in moving it from point A to point B. So this is the physical significance of the line integral of the electric field. Now let's find the expression for the line integral of the electric field. So let's evaluate this. This is the line integral of electric field, RA to RB E vector dot dl vector. Let's try to evaluate it. Let us try to evaluate it. So what to do is, E, remember it's the electric field. It is the electric field at point P. E is the electric field at point P. Here the electric field due to the source charge would be directed in the outward direction. This is the source charge. Now formula for the electric field in the vector form is K Q by R square, R cap. So K is 1 over 4 pi epsilon. Source charge, that is capital letter Q. Distance of the observation point from the source charge, that is considered to be R. Suppose it is R, this distance. So it will be R square. And suppose R cap, this is R cap, which represents the direction of the electric field. So this is it. This is the expression for the electric field dot dl. Fine. So the constant term can be taken outside the integration. So what to do is Q divided by 4 pi epsilon, that's constant. RA to RB will be left with, in the denominator will be left with R square. And this is, remember, this is the dot product, scalar product. A dot B is A ka magnitude multiplied by B's magnitude and the cosine of the small angle between them. Here the magnitude of R cap, that is 1, dl. So it will be dl, R magnitude is 1 multiplied by dl magnitude is dl, and the angle between them. Suppose this is R vector and this is dl vector. This is the angle. Suppose it is theta. So it will be dl cos theta. We'll be left with this. Now further, we need to integrate it, but it should be with respect to R. So dl cos theta is to be replaced by dr. How is it possible? Look, we can drop a perpendicular from here. This is in the increasing direction of R. So this small distance may be considered to be dr. So if you consider this diagram, I'll draw it again for your benefit. This is the increasing direction P. This point is suppose Q, and this is the arbitrary path. This is dl. This angle is theta, and you need to drop a perpendicular over here. So this is dr. This is R. This is in the increasing direction of R, very small elementary portion. So this is dr. So if you consider cos theta over here, you will get base over hypotenuse. That is dr by dl. That is dl cos theta. It may be written as dr. So what we get is Q divided by 4 pi epsilon integration RA to RB dr by R square. Integration of 1 by R square with respect to R is minus 1 by R. So let's evaluate it. So we get Q over 4 pi epsilon minus 1 by R, RA to RB. On further solving it, what we get is Q over 4 pi epsilon, upper limit minus lower limit. Due to this negative sign, we can interchange the terms. So we get 1 by RA minus 1 by RB. So this is the expression for the line integral of the electric field. Now as I have told you, this signifies the work done per unit positive test charge in moving that test charge from point A to point B. So that's a very, very important conclusion. The work done, it depends only on the initial and the final position. It depends only on the initial and final position. It is independent of the path followed. Any path can be followed in moving the unit positive test charge Q0 from A to B, but the expression will remain same. This is the mathematical verification of the fact that Coulomb force, that is electric force, is of conservative nature. Now since it is of conservative nature, obviously it will obey inverse square law, right? It will be a central force, and the amount of work done in making a charge to move along a cyclic path would be obviously